Alors, je voulais juste prendre 2 minutes pour vous remercier tous. Alors, je me présente, je suis Marie-Josée Bache, la vice-rectrice à la recherche, découverte, création, innovation. C'est un grand plaisir de vous voir tous ici. J'aurai des questions pour vous à la fin. Mais en fait, l'idée est bien sûr de pouvoir se rencontrer sur une base régulière, d'échanger, de poser les questions les plus folles entre nous et puis de pouvoir développer un langage commun. Alors, c'est une belle initiative. Je remercie Margarita et Sébastien d'avoir voulu lever le flambeau, tenir le flambeau ensemble et puis préparer une programmation pour la première année. Et puis, donc, more to come, comme on dit. Alors, un grand merci.
So I would like to introduce the next speaker. Joseph Paul Cohen. He has a PhD degree in computer science and machine learning, and currently he's a postdoctoral fellow under the supervision of Joshua Benjo at Mila. His research is in medical applications of deep learning. So Joseph, welcome.
How you guys doing? Okay, so today I'm going to talk about successes with working on clinical data using machine learning and deep learning. We're going to focus on what people are researching right now. So if we take a look at a survey, we can see over the years, starting from 2012 to 2017, publications using deep learning for electronic medical records is on the rise. So specifically, where is it on the rise? In representation learning, concept representations, also de-identification, which is shown here. And then this representation learning, so this de-identification shouldn't have been highlighted. I don't know why that one's there. So if we have representation learning and concept representations as the main topics or like application areas, if we look at the actual techniques used to accomplish this, we can see that it's largely unsupervised learning, as well as convolutional neural networks and RNNs for supervised tasks. But a lot of the work is in these unsupervised models, and that's what we're going to be talking about today. Great. So specifically, what data can we work with? Specifically, that's in an unsupervised way. So we have clinical notes and clinical publications. There's tons of this data. The clinical notes are in hospitals everywhere. Clinical publications are all over the internet. And then what can we do with this raw data to make it useful for us? What are we trying to do or to learn some representation for? So if we think about how we can represent patients with some sort of representation, if we have a lot of notes for that patient, we can say what patient is similar to another patient given the notes written by doctors. How two patients are different in terms of their trajectory and where they're heading. We can also do the same thing for doctors. So maybe certain doctors are treating people with a certain strategy, and we could see that to see the doctors that are similar, doctors that are far apart. Maybe doctors' specialties. We could also represent the specialty of a doctor and kind of say that these two doctors share a similar specialty. So maybe there's like a referral, between them, so you could have better planning in this. We can also look at visits to say, given the visit that's happening today, what do we expect the next visit to look like? If we can predict what kind of maybe embedding that would be, have a representation for this, we can say, given historical visits where this visit and the treatment that was administered after this visit, if that was a deciding element, if that was a very predictive to the outcome of the patient, right? So you can say, you can kind of look at historical visits and look at what happened after them by looking and kind of comparing them in some representation space, right? The alternative is to just read over everyone's medical record in your hospital, but maybe using a distance function would be faster. So we can also look at diseases to say maybe two diseases go by similar names, but they really have the same symptoms. They're really similar, and just maybe looking at and comparing two hospitals or maybe two doctors that are just like using different nomenclature to describe the same things. We could find similarities or differences between diseases. Same thing for drugs. We could do kind of drug discovery with a relationship to how this exists in literature or how this is impacting patients in a specific hospital. And similarly for symptoms, we can find symptoms that are the same or symptoms that are false friends. Maybe they sound the same, but they're very different. So approaching representation learning for these concepts, using these like textual corpuses of data, is a live research area, right? Great. Okay, so what does this representation look like? At some point, it's dots in a plot, right? But these could represent really high-dimensional vectors, and we could do all sorts of stuff with it, which I'll talk about on the next slide. But in the end, we just have these dots where we can compute distances between them, and we can kind of try to draw conclusions about the kind of process that gave us this representation, and hopefully learn something about the data we're working with. So some approaches from the non-medical space that have been kind of behind this embedding kind of world of research. Some of these approaches, so the original WordDevec paper from 2013 established this idea that you could do math on the vectors that represent these words. And you could do things like, you could say that the relationship between man and woman is really similar to the relationship between king and queen. So if you looked at the difference between these, and you took this vector that was between man and woman, and you said, I'm going to take this vector and then just apply it to king and see where we end up, and you'd actually end up at queen. So that makes sense. So if you take king and then apply the same transformation, you'll get queen. And then later people realized that you can also use this to look at relationships between words in the same way with these, but also darker, softer, right? So you get this kind of these properties of the language that you're operating on, right? So these are trained on very large databases for English, and we can kind of play with this idea of the data that they're trained on to build representations that are going to tell us different things. Okay, so that's going to be a theme. So you have the basic kind of representations of English, but we can apply those to other things, like this work by Will Hamilton, where we look at the way words change over time by looking at their word embeddings in text over time, right? So if we consider each word to have a date stamp or some range where it was used in a specific context, we can train one of these models to give us an embedding for the word broadcast in its 1850s use. So all the text that was used to train this was related to its use in the 1850s context. But then you have another representation for a word with kind of a different context. So like this came from books or other literature, like the reference of this word that was used for this model from the 1990s. It's the 1900s, sorry. And then broadcast as it's used today from the 1990s, where this is trained in another context. So if you put these all together, along with the regular words that exist in the same context, in like for all over time, you can see that in the past, broadcast was similar to the concepts of sow, seed, and spread, right? But over time, it evolved to be more closely associated with newspapers, and then today, you see it's affiliated with radios, right? So these concepts are very far apart, but because broadcast, the meaning has evolved over time, the new representation of broadcast is similar to a radio, right? Similar for the word awful. So it used to mean deserving of awe or majestic, and now it's evolved to mean terrible, right? So we can kind of study language with these embeddings too, right? So there's some potential for, in the medical field, of this possibly. although I haven't seen any research doing this study in medicine yet. So we also want to represent these words as vectors so we can use them in other models. This is a little bit of foreshadowing, but if you have a whole paragraph of text, it's really hard to build good representations off of this that are usable. So one thing we could do is consider each word a vector, and we can just kind of sum up all the vectors, or take the average vector, and we can build models by replacing words by this vector that means more about the word, right? And then we can train this on very large corpuses of text, and then we apply it to a small data set, which could be just medical notes in a hospital. You have these rich meanings behind the words that aren't just from your data set that's in your hospital, right? Or some actual data you're operating with. So you get some sort of transfer learning effect with this. Great. So we can also use this in place of words and RNNs for the same approach. And I just mentioned the augmenting smaller data sets. Okay, great. So one piece of background information is how computer scientists want to represent words. It's not how we would think about representing words. So we want to represent it as a one-hot vector. This is like the word in deep learning for how you represent everything. Just make it a one-hot, right? So we have cat, dog, house, and we have these vectors, the length of every word in your vocabulary, and then we're just going to have a single element that's on. It's just a 1, and everything else is 0, right? And this is going to be the basis for what gives us these embeddings or representations, right? Because if we have some matrix, let's say W here, we can use this one-hot representation to just kind of slice out a single column of this matrix, and this column here is our embedding. So this could have a bunch of, it's a real numbered vector that represents the concept somewhere, but we're able to just like kind of slice it out with this approach, right? So this is why we prefer to have this representation. Great. Okay, so we can represent words. Now let's talk about how this word-to-vec model works, right? Specifically, there's a subset of this. This is approach is called skipgram, but for here, we can just generally call it the word-to-vec model. We're going to go through every word in our training, in our corpus, right? So we have, millions and millions of words that could exist in this data set. Think of like every word in Wikipedia, right? And it's in some sentence, okay? What we want is to establish a context for each word. So we're going to have let's say we're going to go through the text, and then we're right now situated on system, and maybe next we're going to start looking at other words. But if we're just focusing on system, let's say that's our focus word, and now we want to say what's the context that we're going to use, right? So we have involving, respiratory, other, chest, symptom. Okay, so here's a bunch of context words. The extent of this is 3, right? So like we have a context size of 3. If we had a context size of 2, it would just go to evolving and it would stop at chest, okay? And how we're going to use this context is to say we have this word system, which is a one-hot vector, right? That we feed into some neural network that's going to compress it down to some latent space, okay? And then we're going to predict the value of another one-hot vector, which is the same size. So it's W is the size of all the words in a vocabulary. This output W is also the size of all the words in a vocabulary. And then we're going to select 0 or 1, right? So this output is going to be a multi-hot, another deep learning word. So that's when you just add one-hot vectors together. Where we have a 1 for involving, a 1 for respiratory, 0 for doctor, because doctor is not in its context, and then 1 for chest, right? So we say, whenever you see system, we're going to embed it in some space here, and then we want the space to output. So this is another transformation, right? And we're going to predict the context of that word. All right, so we're going to generate these context pairs, this focus context pair. So system is going to appear many times in our corpus, right? We might see this hundreds of thousands of times, depending on how big the data set is. And every time is going to have a different context, right? So we can't really generate a model that's going to perfectly predict the context, right? That's not what we want. We want the general solution to this. So like, whenever you see the system, you generate some output that pretty much satisfies the most common context of that word, right? So maybe for only one time in the entire corpus, system is associated with chest. So only one training example contains these ones with the chest one as a one. But all the other ones will be different combinations of ones that represent the other contexts, right? And we want to simultaneously minimize this kind of reconstruction for all of those contexts. Okay? Any questions? Okay. Good. So if we think about this, each word is going to be a training example, right? So system in this sentence is a training example. As we move through it, each one is a different training example. We want to skip the filler words like and is, and the words that aren't going to give us insight. And then each word is going to be used in many contexts. And really, think about this, the context defines the word, right? So that's, when we get some latent space here, what it's going to represent is the context of those words. Okay, good. So if we visualize this training in progress, it'll restart. So it starts in the beginning, and it just kind of starts putting them out. And you can see these points. So you have man, king, woman, and queen. And right now, this is a two-dimensional latent space that's trained. So it's a projection into 2D, and then another projection like out of 2D to the full dimensional, the full multi-hot vector, which is the context. So if you feed in an individual word, it'll give you a two-dimensional point, right, that will then be reconstructed to the multi-hot space where it's going to try to match the context of that word. So if we look at the result, we can see if we take a vector from man to woman, and then we put that vector on king, the closest point in our corpus is going to be queen. And also is, that word there is. So it's kind of a bug in the training, but it did get queen, so it does work. Okay. Yeah. 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 Or the corpus. It's a very small corpus to make it just have this many words. Yes, but that's, yeah, so there's going to be a lot of randomness in training these embeddings. When you get to a really large database of words, then things become more consistent, but for the examples that I have here, everything is kind of tiny. So, especially if you want to get medical records from a hospital, the data sets are really tiny, right? So here's one source of data. So getting access to data for deep learning researchers is very difficult. So if you have data and you want to give it to us at Mila to work with, please contact me. In the meantime, we work with these open data sets. So here's PubMed Central from the NIH's PubMed Central. They have an open access subset. So it's the papers that are published open access, and then they're indexed by PubMed. And they do a great job of formatting them into a document, because you see that on the website they're in HTML, so they actually have this structure of the document parsed into all its pieces, right? So you have like a section that represents the abstract of the paper, and then you can actually programmatically go through each section of the paper. So it's really nice to work with. But you end up getting these big XML files, and you can download all of them with FTP. It's super easy, and we have over 1 million articles to go through, and they're organized in terms of journal names. It's about the granularity that you can get in a programmatic way, because it's pretty wild inside a journal. But this gives you some sort of grouping or label for each document. So we have genome biology, and then a lot of publications under that kind of topic, right? So we can use that to say, this is the topic of these papers, and we kind of know something about the content of those papers, right? So we can kind of reason about this entire field or this journal as a concept that labels all these documents with a specific topic. And we have that for a lot of the other journals. Great. So one thing to touch on now is when we take these different data sets and learn some word representation on them, we're going to have bias in the model that's constructed, right? So in the past, there was a tiny data set that was used, and that led to some bias, where it didn't match everything the right way, but that was because of the sentences that were used to construct those focus context pairs, right? So now if we look at 4 different data sets in the medical domain, so we have medical records from the Mayo Clinic, the PubMed open access subset, Google News, and Wikipedia, right? So if you see, these are kind of technical, and these are going to be kind of non-technical, right? So it's like news articles. They're not going to really focus on the science that's going on in a PubMed article or in a medical record to talk about specific diseases. It's going to be more maybe pop culture or pop health articles. So the representations we learn are going to be different because the context that this optimizer is solving for is going to be different, right? So we can use this to our advantage, as I showed in the Hamilton example. But this is something to be aware of whenever you're learning one of these models. All right, so if we take a look at Word2Vec trained on these different corpuses, you can see, if we focus on a specific target word of diabetes, we see from the EHR records, we see that it finds the full name of diabetes from the medical records. So some doctors were writing out the full name, the full technical name. Where from Google News, so first let me introduce these. So we're going to look at this focus word diabetes, and we're going to embed it in some space. And then we're going to look at the closest points to that vector in that space, right? And just like the top 5. All right, so it's going to be heavily biased by what words exist in the corpus and how they're used, right? So some words in the health records are not going to be in Google News, and vice versa, right? So like the word spaceship is probably not in a electronic health record, but it might be on Google News, and this is going to be a point that doesn't exist here. So we can see that the EHR record is very kind of on point for being more technical, where Google News finds diabetics as the first hit, and then hypertension, which if you look at articles, it says diabetes. That diabetics are at an increased risk for hypertension, right? So there's some link that it found from those articles that were in there, right? We can then look at peptic ulcer disease, right, as a one big token that was used as a single embedding word. And we can find that we find types of ulcers as some of the things from the health records, and then symptoms from ulcers in Google News, right? So I don't have answers for why these are different, but you can kind of observe that there's some bias depending on the data that you train it on. You're going to find different relationships between the words. Colon cancer. So colon cancer is associated with breast cancer. So found this in medical records. Oh, and actually all of them, which is some sort of agreement between these. But then some other things are varying, right? Okay. Good, so another data set to look at is the Indiana University Hospital Reports. This is from the OpenEye repository. So this is a bunch of chest x-rays, and each chest x-ray is a report associated with it. So there's 1,000 reports available in XML format, so we can parse them and work with them. Great. So if we go to train some model on this Indiana University data that's just on radiology reports, we first need to talk about some hyperparameter search that's also going to happen here, right? So depending on the configuration of the model that we're using, we're going to run into like different kind of convergence scenarios on our word embeddings, right? So generally, if we see just a big pile of words like this, we could come to the conclusion that there is no information in this word embedding. So maybe if you just start out with a random network and you haven't done any training yet, it's going to look like this, and it might not contain any information. It could also contain a lot of information, so it's hard to know right off the bat. But generally, if you don't see structure, then it's probably not containing anything. Where if you see some sort of pattern with all your vocabulary words here, you might conclude that there's some sort of compression that was happening, right? So this is the conclusion I'd come to. And there's a lot of things we can vary. So we have the dimensions of the embedding, all right? So for here, it's just 2 dimensions. But we can increase this latent space to have 100 dimensions or 1,000 dimensions, right? Especially if our corpus of words, if our vocabulary is very big, we might want to have a larger embedding space to represent all of them. Also, the learning rate during training, the actual token words we're using, right? So that just parsing the corpus into different words is going to be a challenge. Because you might have two words and you should have tokenized them together, peptic ulcer, instead of peptic and ulcer as two separate token words, right? So this is takes a lot of NLP to kind of figure out the right way to do this. And also our window size or our context, this is also going to make this space look much different. Okay, so some other examples. If we train this on the radiology data and just use a two-dimensional embedding, we'll get kind of this difference from the word spleen. Spleen, we see seen, evidence, infiltrate, right? So, and we kind of see some pattern like this. Where if we take a dimensionality of 100 at that latent space, we can visualize the space with a t-SNE that looks like this. And also we might see more insightful embeddings, although it's kind of unclear what the core difference is between these models, right? Okay, great. So now to move on, let's talk about time series medical records. So the first thing we want to look at is what the space looks like. So we have some event. So if each of these is a visit, we have this time xt minus 1, xt, which is maybe the visit today. This is the patient is in the office today. Xt plus 1, so this is the next visit, and we don't know when it is. We don't know what exact time in the future this will be. And what we want to do is predict the probability of some event in the future. Will this event be, dangerous? Will it be? What kind of intervention will be required here? Will it just be a routine? What will their blood pressure be here? Right? So simple questions we can ask. We can also predict the amount of time it'll take before we get to this next visit. Right? Is it 6 months? Is it 2 years? Is it 4 days? Right? And I guess this comes into planning for your emergency room if you know that a bunch of people are going to come in soon. Also, if you have a model like this, you can find similar patients, right? So if you have similar patients, most likely their next visit is also going to be coming at a similar time, and maybe the kind of events that are going to happen on that time are going to be similar. But in order to work kind of from the computer science point of view, we need to code everything in some sort of encoding, right? So the question is, we need to define what events are. So we have these empty boxes, so we need to fill them with something, right? So a common open coding strategy is the International Classification of Diseases, which is for reporting to the WHO. But what this gives us is a standardized set of diagnostic codes that we can feed into our network as a big set of one-hot vectors to represent these concepts. So some example ICD-9 codes are this. So you can take a look at these. So we have 786, that's the high level, symptoms involving respiratory. And then kind of have some coding below, right? And then for each one of these, if we zoom in a little bit more, so if we go to 786.5, we have a bunch of sub-classifications, right? And this grouping is going to be really useful. The fact that we have all these things are just part of 786.5. We can just kind of group them all together. Or we can go in more detail, right? And as ICD keeps evolving, the codes are getting more and more detailed. So an example from ICD-10 is this code. You can have an event where the person was sucked into a jet engine. Also a Healy's accident. And if you look at the hierarchy above Healy's accident, it really kind of makes a lot of sense. So the super type of the Healy's accident is, it's an external cause of morbidity, okay? It's an air and space transportation accident, right? Pedestrian conveyance, right? So like bicycles, stuff like that. And then it's rolling type, right? So really, Healy's are well defined in this hierarchy, right? So you can really get some detail. Okay. So now we can use this to code all of these. So that with most of these models, the data that they're going to want to work on is these standardized codes, right? There are some other frameworks for standardized codes like SNOMED, but having proprietary codes makes it hard for researchers to just share a GitHub repository and run some code. So it really makes it hard to work with these. Using these open standard WHO codes are really the way to go. Okay, great. Yeah. So I assume it varies in all hospitals. So for there's no. Maybe we can get a poll of the hospitals in Montreal. How many use ICD-9 or ICD? One. Okay. Hey.
When physicians are billing, they are using ICD-9.
Yeah.
But in médicaux hospital database,
Mhm.
since 2006, they are using ICD-10.
Okay. But it's ICD.
All over the board, yeah.
Yeah. Okay. So not ICD-9. So like the ICDs in general. I think they're all good. Not ICD-9 is older now, but yeah. So the newer ones are there. So it seems to be. Is anyone not using ICD codes in the hospital? Okay. Someone else is coding it, yeah. Okay. Okay. Okay, so that's the answer. Okay, great. So how can we work with these codes? So we have these IDs for all these events now. One approach is called MEDDEVEC, where we can kind of predict past and future events and determine embeddings for visits and visits with demographics, right? So we can encode our visits in this fashion. So we take a bunch of one-hot vectors and we add them together, so we get this multi-hot vector, right? That's going to represent the current visit that we've had today. So the current visit is a collection of multiple codes. That's the way we'd like to abstract it. So I mean, there's a lot of other stuff that's not maybe going to fit in here, but generally we have this representation. And what we're going to do is do kind of one transformation into some latent space, U, right? And this space is going to be our visit embedding, right? So this is going to represent our visit without having it be this gigantic one-hot vector, right? Multi-hot vector, sorry. But now we've represented the visits, we want to have the demographics of the patient, right? The specifics for that patient, not just the codes that were registered on that visit, be kind of introduced so we can concatenate these together, run it through another transformation, and we'll get the visit embedding conditioned on demographics. So now this contains the information for this specific visit for this patient, right? Kind of intertwined with the information about that specific patient. And now what we want to do to train it is predict so we have X at the visit now. We want to predict the next visit and the visit before. And we want to keep going, so we'd make this window bigger. Right, so you can predict the next few visits and the visits before. And what this is going to do is kind of give us a representation for visits. And then when you have a visit with a specific set of demographics, it's going to bias like what the next prediction's going to, what the next visit's going to be. Right, so you can kind of gain information from that. Right, so let's look at the numbers. So first, before we look at like a kind of quantitative evaluation, let's look at what we're competing against. Right? So with a one-hot representation of the actual visit embeddings, if we say that's the only representation we're going to use, so just this really multi-hot of the visit, a stacked autoencoder. So if we train an autoencoder to reconstruct the visits, we kind of have some smaller coding that we then use. Right? So instead of learning this end-to-end from the raw multi-hot visit vector to predicting the next and before visits, we'll actually learn a dimensionality reduction using an autoencoder to kind of get a smaller representation for our visits, and then we'll go on to make a prediction just from that. Okay. We can also use WordDevec, So we learn code-level representations from our data. So we say, like, how often does this code occur in different patients? And then we add the representations together into one vector, and then we make a prediction from that. So these are just the general approaches, right? Okay, so it turns out if we do this analysis where these are all kind of going to be the same plots, varying different hyperparameters, or different parameters of the training, where blue on top is going to be this MedDevec model, and also stacked autoencoders are going to be in yellow. The one hot, where we just feed in the data, is purple. And then skipgram is going to be this one in red at the bottom, so that's where we actually train a WordDevec model on the patient visits, right? Generally, they're all the same at the top, with skipgram not working so well. And this evaluation is done on this data set from the United States, right? So this should be from a specific hospital. And what we're plotting is the top K recall. So it's kind of a weird metric. We're going to have the number of true positives in the top K predictions, right? So for this specific event, how many of the events that I predicted would happen, how many were in the top K, right? So here we're going to do the top 30, right? Over the number of actual true positives that I hit, right? So it's a metric that is unique to this set of papers, right? Okay, good. So now let's take a look at what we can do from clinical notes, right? So if we have an example clinical note here, free text from a doctor is going to be really hard to process. Free text in general, there's so many caveats to how you could understand this data. So understanding and getting any information here is pretty difficult, and it's still not working that well unless you have a lot of data. One approach is to use an RNN. So you can feed in your sequences into an RNN, which I'm not going to go over in detail, but generally the structure is you can feed in one word at a time and it processes in some cumulative representation. And after you've read in some sentence or the entire clinical note, you can predict some specific code or a set of codes that would represent that specific visit, right? And why would we want to do this? So we can adapt clinical notes to code automatically, right? Specifically, if you have an old database of data and you'd like to use it for some other predictive models, you could convert just that raw text into something that's coded with the ICD codes. You could also correct errors, right? So if you have someone who's read the actual note and then tried to put the codes in, and then you have a model also do the same thing, and you can look at which codes aren't listed there. What codes are we predicting that the model thought were in this note, but the person who was actually coding this document didn't find? Or something where they added a code, but it wasn't supposed to be there. So you can do this as kind of a sanity check on this coding process. You can also convert between ICD versions using this, because there's not a clear mapping between older versions to newer versions. So if you want to go from 9 to 10, there's many subcategories that might exist in the new data set, in the new coding. So what you could do is use the clinical note to help you make this prediction, to help you upgrade your notes, your codes to the newer version. Okay, great. So another simpler approach without involving RNNs is to just use an MLP to make these predictions for a time event in the future. So if we say within the last 5 years, some events happened, right? So these codes occurred on these visits. We can just group them all together into a multi-hot vector, and then predict the existence of a specific code or multiple codes, within the next year, right? So a specific issue that you want to predict given some historical data. So by binning it this way, the model becomes much easier to write, much easier to run. The data is much easier to work with. Everything just gets easier when you just use an MLP. And this is kind of a basic approach to doing this. All right, so that's kind of a simple approach. We can go back to RNNs and see how they're working on these things. So this paper from 2016 called Dr. AI used an RNN to predict the next event, the next visit, as well as the duration to that visit in this fashion, right? So they would go over the time of the patient, right? So all the visits the patients had, right? And then at each visit, these X's represent the codes for that patient. So in this case, it's a 40,000 dimensional vector here. And what they're going to do is run it through some RNN structure. And then at the output, this Y is going to be the medical codes at the next visit, right? As well as the duration to that visit. And some insight from this paper is what they found is having the input space be 40,000, which includes like just a lot of the ICD codes, and predicting just the high-level categories. So they just chose 1,778 codes to predict, and these are high-level grouped categories, right? So you saw that there were high-level categories like 786. So that whole category would be a single predictor. So every event that could have happened that was in there would just be considered one of those events. And this was critical for making this learn. So they evaluated on this gigantic cohort from Sutter Health in Palo Alto. And the results seem okay. So if we look at this recall at K, it's 72, where they claim these other models aren't working so well. Maybe these numbers aren't high enough for how people actually want to make predictions, but they're getting there, right? Okay, one other insight from this paper is that there's a small data set called Mimic2 that they used, but there's now Mimic3 in this kind of Mimic series of data sets from MIT, which are just emergency room visits, but it's pretty small. There aren't that many patients, and there aren't too many visits. And they found pre-training using this large cohort of data sets from the Sutter Health data set, and then training on this Mimic2 data set allowed the model to perform significantly better than if it was just trained on the Mimic data alone, right? So having large data sets to train on has an impact, right? It's definitely worth it. All right, so we can see that this red line is just on Mimic2, and then once the results on Mimic2 after being pre-trained, so all the weights have already been trained on the Sutter Health data, it kind of immediately gets good performance in comparison. Okay, good. So some related work here. All right, so moving on to kidney survival event prediction. Am I looking good on time? No, okay. So if we want to estimate if we want to pick between a few kidneys, right? So we have kidney A, kidney B, and kidney C. And we have these attributes about the people, right? It's very simplified, so normally you'd have more, right? How would you want to pick between these kidneys? Which one would you suggest to your patient, right? One approach is to just look at a risk score, right? And maybe this one sounds good, right? But then you wouldn't want to choose these, right? So, but this single number is not too interpretable, right? It would be better if we had like kind of an actual approximation of the survival curve of this patient, right? Some sort of way to visualize the outcome of this patient. So if we look at predicting the actual risk, right, over time, so if we just look at the probability distribution of the patient who received this kidney, that they'll reject the kidney graft, we'll see that it's pretty constant for this case. So if we look at the actual survival for, let's say, 20 years, right, it's pretty constant risk. Compared to this kidney, which has a higher risk, so we can see that there's a higher chance that the kidney will be rejected at the beginning after the transplant, and most likely there won't be any risk here because the risk is already so high that they'll have completely rejected this kidney. And then this one looks pretty good. So there's a very low chance, and then it kind of rises in the future, right? And we can see this if we look at the cumulative distribution, right? So in this work, the idea is having these more interpretable survival curves are going to make a difference in selecting which kidney and treating patients, right? So the details from this work, from Look in 2018, was that we want to predict this cumulative distribution of survival, but there's some challenges where you have censored patients. So after some time, some patient might drop out of a study, or they'll withdraw well, if they withdraw their consent, they're gone from the whole thing. But they might vanish, and you don't have any information if the actual event occurred, but you know the last date that the event did not occur, right? So we have kind of a true event for a patient. So given some demographics, we have the true time that an event occurred. So we have like a true CDF, right, where they're fine, and all of a sudden, kidney's rejected, okay? Where one way to deal with the censored cases is that we know that they're fine, and then they're censored at some point. And after that, we can only estimate what their kind of chances of survival would be given historical data that we have from our data set, right? So you can say that that's kind of the global distribution of what happens to people who have lived or have survived with their kidney that long, okay? And kind of with this trick, you can learn to output a distribution using the Wasserstein metric in kind of this form. So we have the output of a CDF from some model that's generated from a neural network, and then we just take an L1 distance, right? So just a bin-wise distance between these two CDFs, and this is sufficient for training a model to actually predict the survival curve. Okay, great. All right, so another cool piece of work is this medical NLI, so this natural language inference. Do I have time? Okay. Yeah, okay, so I'll skip over these. And then some talking points. Maybe I'll just hit the last one. All right, so where a lot of these studies claim state-of-the-art results, they can't be verified by external parties working on them, so this is really a barrier to doing research, because we can't validate or invalidate that some method worked on some data, right? So there's a necessity for some more public health data sets involving medical records so we can actually validate that people's approaches work or not, because otherwise it's just trusting the plots in a paper, which I don't enjoy doing. Great, so I'll thank the team at Mila Medical, and any questions? Yep. Yep. Mm-hmm. Exactly. Yes, exactly. So there's like in these slides, this research had tokenized this entire phrase. So this was the word. So this received a single one-hot vector. Yeah. Yeah, because you want the concepts to be the tokens. You want the concepts to be the actual points that you're embedding. Like you want a representation for a concept. The words are a proxy because we kind of think they're the concepts, right? Yeah, so you'd want to parse like with some sort of grammar so you can say that this is the subject. It's like this whole phrase. Okay, yeah. And you can consider that a token? Okay, yeah. Yes, I mean to make a higher level. Okay, yeah. Yeah. Okay.
Just to follow up
being passed on over the evolution process.
It sounds like a good idea. I don't know of anyone doing it, but I
Aware of that? We have a good group of evolutionary biologists here. People who could test whether, whether evolution and genes being passed over during evolution could be a model system that could be treated as a language.
yeah, like a gene over time.
Yeah.
Where what was its context in, a million years ago, and what is its context now?
Or from, like a prokaryotes to eukaryotes to higher order individuals, and how the way you picture, how words change over centuries.
Yeah.
Genes evolve in ways that, their function changes over time and over species. So
Yeah, yeah.
this has been looked at.
I don't know. I like it. That's the next talk. That's good. So someone hurry up and do that research so we can present it. Yeah.
Do you know, I'm coming back to the ICD-10 where you predicted time plus one, but we're trying to do something similar but with mental health outcome, and it's much more difficult to predict what will happen to a patient in a mental health emergency. Do you know some study that successfully predicted specifically in a mental health emergency room?
No, I'm not aware of one.
Because the ICD-10 coding is kind of not working as well as in the other physical health.
Like the coding might not be
to
right.
find some other classifications, so I was wondering.
DSM and
Yeah, I know, but the ICD-10 is
No, they
kind
are
of-
not the same code.
it's not exactly the same, but it's not working as. Yeah.
Yeah, so you could take these models and do that. So I mean, there's nothing stopping you from just appending onto this vector more codes to represent that visit. You can just keep adding more data, and then it'll predict it. Right? So you could augment it with other classifications that would capture those aspects of the visit. Do you have another? Oh, yeah. So it's the next visit, right? So Y hat should be the visit that's going to happen next, and it's the high level codes. So it's not. So we have the granular codes here, and then we'll have some like reduced complexity at the prediction. Yes, yes, it is. Yeah. As well as some other ones. They throw in other codes. So like yeah. Yeah. Yeah, if there's like no representation for a lot of codes that are in here, you wouldn't then not be able to benefit from that on the other data set, right? Yeah. So I mean, it depends on like. Okay, yeah. Well, so that's what they encountered here, right? So like the network could learn how to group these codes at the input, but then at the output, it wouldn't know how to predict because maybe just the loss was kind of configured wrong. Because they would group them together, and then it just had to predict anything in that region. Like it could group a lot of things at the output, and the penalty, the loss function, was just on a specific error on a specific high-level category, instead of it's like a bicycle accident versus a Heelys accident. And it might get it wrong, but you could just group them together, and then the loss is applied to that general category, and then it's not really wrong. So you're really just matching the expectations you have on the output, right, for what is wrong, right? I think there's maybe other different approaches where you do more hierarchical losses, or you do some sort of grouping in the loss that you're trying to predict. So you just penalize your errors differently based on how wrong they actually are. So there's other work where you say, like, if you're doing image prediction for people, you have a young person, a middle-aged person, and an old person, and your network predicts young person and old person, but not middle-aged person. It's probably something that's not correct, right? You should, if the actual true class is like a middle-aged person, and you predicted young and old person, you're not really wrong. I mean, you predicted a person, so you're pretty close, right? So your kind of prediction should meet some kind of expectation where you're not penalizing things that are close to being correct, right? Yeah, so. Great. Thank you.